Yeah. Okay. So good afternoon, everyone, again. Welcome to this edition of the NITheCS Colloquium. This afternoon, we have Professor Zurab Janelidze with us. Zurab is a professor of mathematics at Stellenbosch University. He's also the president of the South African Matematika Society, editor of very important journals. He's passionate about all aspects of mathematics, including teaching and learning. Yeah? And Zurab is here today to share some new visions on how to teach and learn mathematics in the future. Yeah, so Zurab, thank you very much for being with us today. And we are very curious to hear what you have to say. Thank you.
Thank you very much, Francesco. It's always a great privilege to give a NITheCS Colloquium talk. And thank you very much for everyone for being here, and those who are online, and perhaps those who are going to be listening to this talk far in the future, because all the talks are on NITheCS YouTube channel. The title of the talk, as you see, is A New Horizon for Teaching and Learning of Mathematics. I certainly do not want to have any prescriptive tone. I just want to report on some of the developments in collaboration with various colleagues across South Africa, where we are thinking of new ways to get mathematics across in a state of mathematics in South Africa where we have some serious challenges. So basically, the talk is going to be a series of lessons that we learned. And the first lesson relates to a course in mathematics called Foundations of Abstract Mathematics, which has been running at Stellenbosch University 2012. There are two courses, the second year course and the third year course. It was initially intended to be an elective module in Stellenbosch University. We call the course module. That's part of the mathematical sciences program. Eventually, it ended up being one of the modules for a specific stream of study in the mathematical sciences program. And everything we do there is quite different to the usual way of learning mathematics in several different ways, and I'm going to speak about some of them. So yesterday, I told class this course that I'm talking for today and asked for their input. Two students responded immediately, want to read to you their input. I think the impression about the course is best communicated through the students. So there we are. Afternoon, Prof. Thanks for giving us the platform to learning in a new way. I'm personally coming from the chemistry perspective of theory-based learning last semester. When you called me for engagement with solutions I wrote for the set theory test, you pointed out a very important point, that you lack the basics of understanding the language of mathematics, and your work is so hard to understand without your one-on-one explanation. This is me talking to the student. I must be honest, I was quite nervous because the student has written a lot of things in his test, and it didn't make sense to me. But after he talked about it, it made more sense to me, and I wanted to kind of appreciate the effort that he put in. But I don't think I managed to do that because, as the student writes, I went out to my place crying tears. I was so heartbroken and didn't want anything to do with mathematics anymore. It was so painful and difficult to understand. But all I can say now, Prof, thanks for your words. They really did unveil the real person I was meant to be as a student and as a future learned intellectual. I realized that your teaching approach is too personal, and it builds one's desire to improve their ability to approach, their ability of approach and problem solving in a reasonable way. I can safely say you've opened up a dimension and approach to teaching and learning, not only just mathematics, including all subjects taught at the tertiary level. Yes, this is a new thing to emerge from someone in the academic space and not some political space. That is a very interesting remark. Your work is very phenomenal. I put the blame to myself for not putting the effort in the Foundations of Afrika Mathematics course, but I have learned from my mistakes and I'm willing to come back full on and maybe have sessions with you to see how well I progress with the module. There's a bit more. Your approach to give students enough time to work on their own with the help of tutors who are our peers is very good, since this gives us the opportunity to engage actively, especially students who are scared to ask questions during the lecture. On the other hand, confidence is built from seeing how we fumble along the journey. You've mastered the art of philosophy in mathematics. Now I no longer view mathematics as a subject, but like you said, a concept. You've taught me, amongst other things, the urge to challenge and criticize my work at best that I can. Funny enough, I was the class representative for physical chemistry last semester. And one of the days I approached the lecturer and advised her to approach the module in a way that enforces teamwork or collaboration, so to speak. I want to make an introduction there. It's Dr. Sophie Marquez, our colleague Mathematics Division at Stellenbosch University, who was a very strong promoter of group work in mathematics classes, and I've adopted that philosophy of hers. I was kind of maybe converging to that slowly, but after her convictions, I was much more brave to propose that, and it worked quite well. We have some group work assignments that work very well. Without negligence, we had tutorials every week, and we were divided into groups so we can share our ideas and how we solve the problems we were assigned to each Wednesday. I then went to her office towards the end of the semester, and she was impressed with the type of engagement and also the results improved using that method of collaborative learning. Lastly, Prof, I would like to say it's very important for the Faculty of Science to try to adopt this way of teaching and not just focusing on producing graduates who lack the skill they were meant to master during their studies. This I would like to call a collaboration and skilled approached learning. And so this phrase he puts in capital letters, collaboration and skilled approach learning. I never talked about this in class, and yet this is one of the guidelines for the philosophy of teaching in this course and other activities I'll share with you afterwards. One last thing, Prof, I'd like to say thank you for your passion in mathematics, and not just that, but for the fact that you know and understand what you're doing. Your approach is not just cram, pass, and forget approach we're used to, but a method that allows individuals to pay attention to detail and reason with caution. I also have another feedback to share with you. This is an audio feedback, and unfortunately, due to technological issues, you might not be able to hear it, but I'm going to say afterwards what it says if you cannot hear it.
I thought I would give some feedback on our course and approach to teaching math, because it's definitely an approach that I've never experienced before. So first of all, I believe that something that makes our lessons so enjoyable is the fact that you're also passionate about what you teach. And I almost feel that this love for mathematics is an integral part of making the style of teaching work. If the person teaching sort of is not passionate, then this approach can fall flat very easily, because this love for math sort of acts as an inspiration for students to then want to put in effort, want to understand and to think. And then in class, there's also this feeling of patience, as if there's this understanding that not everyone moves at the same pace, which I personally love, because it creates a safe environment for learning, and it's okay to make mistakes, which usually in math class I don't feel like it is. But I have a feel that this love of maths is not going to encourage everyone, and a lot of students still only have that aim of passing. So with this style that our course is providing, I feel like a student can be sort of fall into one of two categories. So there's higher than people that like the style, and you like it because you choose to learn and you choose to grow and use all the opportunities to show your hard work. You find the style very challenging because there's a lot of responsibility that falls onto you as a student. It's not just something that you can learn a bunch of things and do well, or you can't just show up to class and then listen with heart. Like you have to think, you have to get your mind into the right space and truly in the lesson try and like figure out this puzzle almost and understand what is actually. So I think that's the style of teaching is super, super cool. And I'm so privileged to be able to experience it. But I also feel that it's simply just not appreciated by everyone. I'm not sure if this is exactly what you were looking for, but I thought, yeah, I would just say it anyway. And I hope you have a good day.
Were you able to hear it at all? Oh, that's fantastic. What about the online participants? Okay, so the online participants couldn't hear it, so I'm going to summarize what was said in that short video. There are a few very interesting points that Zia made. She talked about the approach to teaching and learning in this module being quite challenging. She talked about the class being quite intensive as well, that you have to put all your attention during the class in order to make progress. And then she also talked that about the fact that because it demands so much from the students, the only way to achieve success in teaching that way is for the students to be to have strong motivation for engaging with the work. And she talked about the lecturer's passion for mathematics that comes strongly across to class, and then that gives them the motivation they need for tackling the course. And she did say at the end that there will be two types of students: ones who get excited to concentrate on the course, and the others who just want to pass the course. And for those who just want to pass the course, this course is going to be very, very difficult. But those who are kind of triggered by that passion for mathematics and want to put all in, like herself, it's a very, very new and a very nice experience. There are a few other comments that I've been collecting over the years. Here's one of them. Instead of repetitive information, the lecturer gives us information and lets us build on it while learning from each other. I wish other modules were like that too. This is from 2021. And I want to show you now some sample assessments in this module. So there are assignments and there are tests, but they're slightly different in structure to what we're usually used to in mathematics class. And an assignment, for instance, the one that you see on the screen, this one has 3 sections. The first section asks to provide solutions to one of the tasks, which is writing up a proof for a theorem. It's a theorem they've seen before. It's a theorem they've practiced in the tutorial. And so they have to write down their final version of a proof for one of the selected theorems. Then in section B, they're required to make their own theorem and prove the theorem. So the material that was given to them is incidence geometry, which is basically Euclidean geometry, only the incidence part of it where we only investigate when points fall on lines and when lines fall on planes. The axiomatic system was revised by Hilbert. So it's a fragment of Hilbert's approach to geometry. They're given the axioms. They're supposed to interpret these axioms and apply them in proving theorems. They're also given 15 theorems, and after that, they're also expected to come up with their own. But they didn't practice coming up with their own theorems during the tutorials. At the tutorials, they only practiced proving the theorems that were given to them. But in the assignment, that's where they have to come up with their own theorem and prove it. And then the last section is to include the list of proofs they've done on their own throughout the term with the draft work, and just to kind of have an idea how much work they've put in this assignment. And then the marking is in 3 categories. The first one marks ability to compose correct proofs. So that's out of 5 marks. And that's mainly based on section A. It's an assignment, right? So they could have got some tutors' input on that. And if they're dishonest about it, it'll be difficult to tell. That's why we don't have only assignments, we also have tests. Now, the second category of marks is completeness of proof. So a student might be very thorough in their work, but make some mathematical mistakes. And so to distinguish making mistakes and being thorough, there are these 2 categories of marks. And then the last one, the last 5 marks, is for creativity and effort. And this is where, if a theorem they came up with was quite complex, then they would get some creativity marks on this last category. So as you see, the marks are rewarded not for their answers. The marks are rewarded for skills demonstrated. And something similar applies to the tests. Here is a sample test where they had 3 tasks. And by the way, it's not just a single, it's a test series. So they write a test. If they're not happy to hand it in, they write another one. And this process continues until predetermined number of times. So there were 4 in this specific instance. The first task in the test is to illustrate the validity of the theorem on an example. The theorem will be given to them, a new theorem every test. This theorem they have not seen before. And they have to illustrate the validity of the theorem in intuitive terms, or on an example like it says in task 1. And in task 2, they have to provide illustrations for the intuitive insight to the theorem. And I'll also give an intuitive explanation. That's actually where that happens. In task 3, they have to provide a clearly structured formal proof of the theorem. And once again, the marks are based not on their answers, but on the skills shown across the 3 tasks. 5 marks for ability to concretize, ability to unpack the detail. This is one of the key skills for mathematics, maybe also other subjects. And this is where many of the students struggle. They struggle to go into detail. So 5 marks for that, and then 5 marks for intuitive understanding shown across all tasks. Some students are able to have a very good understanding why the theorem should work. They can even explain it in words, in lengthy terms. But as soon as you ask them to write a formal structured proof, they completely fail. So to distinguish these 2, we've got the second category for intuitive understanding, and the third one for competence in the formal mathematical reasoning. Of course, it's the formal reasoning that allows you to confirm that your intuition is valid. So the third step is very important. Great. Now, out of this experience with the Foundations of Abstract Mathematics modules, which is not only taught by me, we have a group of lecturers every year, and some lecturers come and go, and some others stay for the many years and teach throughout these years. What I've learned myself from this experience is that teaching and learning of mathematics is more effective when anchored at developing mathematical skills rather than accumulating knowledge. In tests and assignments, the skills should be assessed rather than the answers or methods. Now, the thing is that when you ask a student to get the correct answer, or even have the correct method for getting the answer, there's a shortcut the student can take. And this is the wonder of our brain, which is in some sense even more advanced than ChatGPT. So if you feed in enough number of examples of worked out exercises, our brain can work out an exercise without having any idea what's going on. And in a way, that's kind of the failure of the standard examination system, that we are marking for answers and methods, but in fact, many of the students are getting them because they've trained on past papers or the tutorials, since we only really show questions in the exam that are similar to tutorials or the past papers. And so instead of marking that, rather mark the skill, which is almost impossible to imitate, especially at the test. I mean, for the assignments, they could have gotten some help from each other, but at the test, you will really see what their skill is. And that measure of the skill is a much better measure of their overall success in the course than usual exam type of mark. And by the way, the marking of assignments by rubrics was something that, like you've seen before, is something that, again, I was kind of converging in some sense, but then I was reassured that this could actually work when I saw Dr. Benjamin's marking style with rubrics. That was really a big inspiration for me to go a few steps further in the rubric style marking. So Ronaldo is presenting a section of the third year Foundations of Abstract Mathematics module for the last few years. Now I want to move on to the next adventure. So in July, in my role as the SAMS president, I co-organized a gathering of various national societies and entities within mathematical sciences, and we invited Professor Jonathan Jansen to talk to us. Professor Jonathan Jansen is a very famous scholar. He is also the president of the South African Science Academy, and he gave absolutely beautiful talk. If you've seen him talk, you know how inspiring his talks can be. And then immediately after the talk, he published a column in actually not just one, but several newspapers, online newspapers, where he kind of wrote up the content of his talk. He was talking about the following theme: math teaching in South Africa just doesn't add up. And he gave us his perspective on why does he think that teaching of mathematics doesn't add up. And it was a series of reasons. I will only point out a few in the next couple of slides. I'm just going to read what's written on the slides. I decided to address the elephant in every classroom. Why are so many South African children struggling with mathematics? First, because mathematics is taught without meaning, as a series of operations and little more. Now, his comments are mainly based for primary and maybe later on school, high school education, not so much at university, but a lot of his comments, I think, also applies for university teaching and learning. So the teaching of mathematics without meaning as a series of operations and little more, this is real, and it's not necessarily specific to South Africa. The way I've experienced that is, first of all, I've taught it that way. And then I was starting to discover it actually doesn't work. The students are not understanding anything. And then over time, I've been getting feedback from students telling me that they really appreciate the philosophical insight I give during the lecture. That's when I started to see this component being a real component in terms of impact on students. When you're learning something, you want to see the story. You want to have the insight to it. Just looking at the symbols is not enough. But surely many good lecturers do that. I mean, everything that is listed here doesn't apply to every single mathematics lecturer, right? Second, because of the fear of failure in mathematics, and that's a very strong thing. Once I was interviewed by radio on this very topic, there is this fright for mathematics. Ours is a risk-averse society, and in classrooms, we stress not experimentation, but the right answers. You're made to look stupid if you get the answer wrong. Children sense that education is about the right answer, and so they are terrified about looking silly in a class of image-conscious teenagers. And then the list goes on. The seventh on the list, you can look at the full article if you're interested. The seventh on the list is because of the enthusiasm gap in teaching any subject. You can solve most of our backlogs in science or math with teachers who match competence with enthusiasm. Ever watch a South African teacher or lecturer? Most of them, not all, look as if they have lost a relative. you sense a burden on their backs. The children observe the misery on their faces and make an early calculation. This is not a job I want one day. So what lesson have I learned from this specific presentation? Well, once again, something that was there in the subconscious mind, but became very vivid after this presentation. For me, that was the fact that passion for mathematical insight is actually the only framework for effective teaching and learning of mathematics. If there is no passion for mathematical insight, if that's not like the ground foundation level, then everything you're building after that will easily collapse. And it's not just passion for mathematics, it's passion for insight as well. Third story, in January, I took up the question of an alternative mathematics program with participants of a summer school. This was a SINPA summer school called Logic at the Intersection of Algebra, Categories, and Topology. And it was actually co-organized together with Mathematical Structures and Modeling Research Program at NITheCS. And there we had a series of meetings after the main program of the school, where an idea was conceptualized to introduce the meta-curricular international, hopefully, program in mathematics that is not based on obtaining marks, but instead is based on cultivating interest and passion. So we acknowledged there, when we discussed this a bit, and we acknowledged that the drive for marks, which is a very important ingredient of modern education system, it's difficult to get rid of that because it feeds in the drive for money. And it's difficult to convince humankind that we should think in different terms other than money. And if you try to do that, that's probably going to take a few centuries to achieve that. So instead of trying to fight that, let's have something alternative which fills in the gaps that are left by that approach. So that was the idea we conceptualized there, but we couldn't come up with a name. We thought of calling it Art of Mathematical Reasoning or various other options, and we really struggled with the name. And then I told about this to Cerene Rathilal. She is currently a lecturer at the University of KwaZulu-Natal. And she had some very nice ideas to add to this. And she immediately proposed that we kind of start this off in the form of abstract algebra holiday program at NITheCS. I want to show you two snapshots of what's going on in that holiday. It's an absolutely amazing thing. We had absolutely positive, very, very positive feedback from school learners who participated in this program and are still participating. Let me show you to give you a sense of how mathematics is approached here. And again, we might run into the trouble of hearing. So yeah, I'm sorry about that. I'm going to summarize what will be told afterwards.
A series that we plan to run the entire year and in the years to come, and something that we've already run in April this year. So I am Cerene Rathilal, and with me today
So in this first video, I was just meant to show you the disposition of the speaker, a very friendly and positive disposition. And then in the second video, I want to show you a little fragment of the lecture in the middle, the kind of topics that are discussed there.
first set. First set, I've got 1/2, and I've got 1/4. Are these two things the same element? How many elements are in this?
vector set if they are not two. So there are two elements, they are not the same. So there is two distinct elements in the first set. How many distinct elements are in the second set? So can they be four? Just based on that. You see, they don't have the same amount of elements, so they cannot be exactly the same because they don't have already the same amount of elements.
So what was happening there is that the presenters, Cerene Rathilal and Sophie Marcus, were recapping some basic set theoretic notions that was covered in the first two sessions in April, and this is, I think, July session. And so an example of a set was being considered where elements are fractions. And we had set A, whose elements are fractions 1/2 and 1/4, and another set B, whose element is 3/4. And some students thought that they're the same set because when you add 1/2 and 1/4, you'll get 3/4. And so at this point, they are going to explain that in a set, you have structureless collection of entities. You don't want to add them. You don't even know that you can add them. It's just to illustrate to you the level of detail and kind of depth, which may feel like very simple, of course, but believe me, even in the second year, these kinds of questions, students do not know how to approach, even if they've done first year crash course on set theory, because you cannot do set theory in a crash course. It's a lot of deep concepts, and you have to do everything thoroughly to build up the language, first of all, and then to start manipulating with it. So the pace may seem very slow for somebody who comes from, let's say, third year university education, but when you start listening to the whole video, you will see that there is a lot of depth and a lot of thinking skills unraveled in this slow pace, which could also be useful in attacking other content. So we had a grade 11 mathematics literacy learner watching this presentation for the first time. She missed out the first two. Even though she missed out the first two, she could catch up on the third one, which was a recap of the first two. And this is what she said about her experience. I understood mathematics in just a simplified manner. During this program, the speakers helped me further understand and develop my mathematical skills. The speakers made me feel heard with my questions and helped me further understand my mistakes without belittling my thinking. It gave me a great platform to explore mathematics in a way I understand and enjoy. Notice that she says nothing about set theory, because for her, this was not a lecture on set theory, this was a lecture on how to approach mathematics. And that's kind of the spirit of what we're trying to do here under the Future Mathematicians Programme, which is the excellent solution to the name of the thing we conceptualized at the SIMPA workshop that comes from Cerene Rathilal. And she's also heading the program. You will see here what are the goals of this program. Basically, as I said before, it's going to be a meta-curricular program that's going to be embedded in school and university as an additional extracurricular activity type of thing, where the focus will be on a nurturing correct approach to mathematics. But now, in order not to create clash with the existing teaching of mathematics in existing courses and subjects at school, we will be choosing topics which do not clash with the other topics, so that the learners cannot say, but my teacher told me that, and when they go back to the teacher and said, but that person, the university lecturers said that it should work this way. And so not to create this conflict, we're going to be selecting topics that do not clash with the school curriculum. And you see there in the bullet points, so the aim is to use deductive reasoning to make a conclusion and explain. So these are the skills that we want the learners to acquire through this program. Describe mathematical ideas in an intuitive mathematical language, converse in the language of sets and mathematical structures. The term mathematical structure can be new for mathematical scientists. Applied mathematical scientists don't use this term. We have this term appearing in the name of the research program at NITheCS, but it's not a term that we invented. If you look at the national, the American national vision for mathematical sciences for 2025, it talks about mathematics in the language of mathematical structures as well. It's a term that comes from pure mathematics. Then there is a term that comes from applied mathematics, which is modeling. And that term also has a meaning in pure mathematics, but pure mathematicians don't often use that term. So one of the ideas there is to adopt these two terms coming from two different realms to have a common language of discourse about mathematics. So structures and modeling. And so on. There are other bullet items here that I'm not going to go through now. You can have a look at it yourself. And what is the lesson learned here? Well, for me, it was that, especially after watching these abstract algebra sessions. So I've been kind of teaching set theory and logic in a similar style to Sophie and Cerene for many years, but I have never attended anybody else teaching these things. I don't know how other people teach these. And when I saw Cerene and Sophie teaching this content online in abstract algebra, I was so excited and thrilled to see the similarities of our approaches. It was really remarkable to see that they actually do more or less the same thing that I always did. And so that's when it clicked for me that set theory and logic are not only a solid foundation for formal mathematics, which they are, but if correctly approached, can also serve as solid foundation for learning mathematical thinking already at the school level. Now, why do I say here, if correctly approached? Because there was an attempt around the world, including South Africa, to replace the school curriculum with set theory-based curriculum. It was a complete failure. One of the reasons it was a failure is because, I think, that's my impression, it was again taught in this meaningless way, and the teachers were not experienced with it, and the parents were not experienced with it. So many issues there. So it's very important to do it correctly. And the abstract algebra sessions kind of give an example of how it can be done correctly based on the feedback we received from the learners. At this point, I'm curious how I'm doing with time. Thank you. Next adventure. In 2022, together with collaborators, we have started developing mathematical exploration activities in a mathematics club setting. So if we are talking about a meta-curricular mathematical program, we need to develop ideas on what to do there. We need to develop, I don't want to say content because I don't want it to be so restrictive. There should be space for creativity, but we still have to have some kind of idea. What kind of way are we going to explore mathematics with learners? And now this ties very nicely with a PhD study of a joint student of Dr. Erno Lampen and myself, Noluntu Bart. She works for Department of Education, and she's a subject advisor overseeing quite a large number of schools in Port Elizabeth area. So you see here Noluntu Bart on your right, Erno Lampen in the middle, and Dr. Charles Sipper from Tshwane University of Technology. The four of us in different groupings have been developing this idea of mathematical exploration. It started with Noluntu and Erna and myself, where we, for the studies of her PhD, I'm not going to go into what specific topic is for her PhD, but as a byproduct of that, we arrived to a type of activity that's implementable in an outside of class environment. And I want to show you a couple of them. So every activity has a theme. The theme of this specific one is a flower. This was designed mainly for primary school learners, but it also for above primary, also somebody in their 70s or 80s might want to try this out as a kind of puzzle. In the first display, a concept is explained. In this case, is the concept of number permutation. Well, you know surely that number permutation is an arrangement of numbers, and that's what this text aims to explain. Note that at this point, it's not about the rigor of the concept. We actually want, as part of the activity, learners to develop their own rigorous understanding based on this explanation here, and also the activities that follow afterwards. These are very much explorative type of activities where, instead of giving the learners the end product of the definition, you give them the direction, and then part of the exploration is to come up with precise mathematical definitions. And then the activity itself has the first exploration, the following. So there are two flowers. Each of them have petals numbered from 1 to 5. And you want to cut one of them out and match on the second one. And every time you do the matching, you will get certain number matching to 1 on the second flower, certain other number matching to 2. And you record that sequence of numbers you get. That will be a permutation. Now, the different ways you can do the matching will reveal to you the symmetry of the object. If the object, in this case, flower, is symmetric, the more symmetric it is, in a sense, the more ways you will be able to. So the idea here is that permutations allow you to classify symmetries. And the more of them you have, the more symmetry does a shape exhibits. And this idea, this link between permutations and symmetry is to be discovered by the learner, is the goal of the exploration. So the exploration reads, permutations can be used to analyze symmetry of a pattern. Cut out the top flower and match it on the bottom flower in such a way that each numbered circle is positioned on top of another, possibly different numbered circle. Explain how you could describe such matching as a permutation. And in one of the later activities, they are supposed to classify all possible permutations they can get by the matchings of the flower, and they will not be all of them. For instance, you can never get permutation with 1 followed after 3, because there is a 2 in the flower between 1 and 3, and you cannot squash the flower. So not every permutation will describe a symmetry of the flower, only some of them will. And so you can then make a list of which ones will, and that's an interesting activity of its own. Here is another example, but before we go to that, the same learner who gave us feedback on the abstract algebra session, after completing this 3 hours, it was actually exactly 3-hour session of exploration, the one I showed you about the flowers. This is what she wrote after that. I had a complete disconnect with mathematics. I viewed mathematics only for intelligent people and failed to see mathematics anywhere but in currency. After our first exploration, I was completely convinced that mathematics was everywhere and can be applied by everyone. I started understanding that with logic and real understanding of the concepts, mathematics can be easier for everyone. I learned to ask for help, read to understand, not to finish, to apply logic to my work, and not box my thinking in what I'm taught at school. Here is another activity where you see 2 areas drawn there. They need to be tiled. And you almost literally give a theorem. You see, a mathematical theorem consists of assumptions and conclusions. And we never explicitly talk about the structure of a mathematical theorem, even at the university. And it's very important for a child learning mathematics to understand that there are 2 kinds of mathematical statements. Those that are assumptions, those we don't prove. We still want to understand what they say, but we don't prove them. And then based on them, we prove other things that are conclusions. So the assumptions here are that the smaller rectangular floor has been tiled. The robot must tile the bigger rectangular floor with tiles of the same kind. And then the conclusion is that the robot will need 288 tiles to tile the bigger floor. So you see, in a typical mathematical exercise, you will ask the student, how many tiles will the robot need to tile the bigger floor? And so the student will have to figure it out and then give you the answer. Now, this process of figuring out and getting to the answer doesn't have to be very precise. Very often, we arrive at the correct answer by an imprecise, intuitive way of thinking about things. So what we are doing with this activity, we are turning things around where the answer is already there. But now the student needs to explain why is that answer the correct answer. So at this point, the student will have to very thoroughly check every single step of logical reasoning and confirm that for sure, every single conclusion, intermediate conclusion we make for sure follows from those assumptions until eventually it leads to the conclusion. And also, this is done in a group of, let's say, 4. So they discuss this among each other. And after that, they write it in a book. And we have some samples of these books. Fortunately, I cannot hand them out, but I can show them to you afterwards if you want to look through. So this is how they look like. And there are spaces to write in the books. So the robot one is here. The first stage, they actually don't even do anything. They just read the proposition, the theorem, and they analyze it without having any specific task assigned to that, which is there for them to learn to read text and reflect on it. And then on the other page, the exploration of explaining why the conclusion is true is prompted, and then they have to write their answer after they've deliberated this in a group. So these are just examples of activities that can be run in the framework of after-class activity. So specifically, there are mathematics clubs that are introduced by a famous South African educationalist. I forgot her name at this point. I apologize. Nolunte Bart was her master student, and she implemented a lot of mathematics clubs, these are called. And now in that club space, we are implementing this. Here is another example of an activity of this kind. The theorem in this case is a bit more complex. There are numbers that are being arranged by the astronomer. So the numbers are being assigned to the stars by the astronomer. And there are one of the 3 rules by which the astronomer assigns the numbers. We don't know which one, but we know that one of them works. We don't know, maybe 2 of them work. And at the end, the conclusion says something about the arrangement of these numbers. So the learner, to confirm the conclusion is true, the learner first will have to come up with this idea of excluding some of the rules based on the numbers already shown. So that's the first deductive step, to exclude some rules because the numbers already shown do not fit these rules. And then they will end up with one rule. And now they're for sure they know that rule must be the correct one because we are told in the assumptions that one of them is correct. And then they can apply the rule and see whether the statement in the conclusion fits with the rule. So it's a 2-level deductive process here. So what did I learn from this? Well, actually, this was a very impressive discovery that Nolunte, myself, and Erlampen we made. We realized at some point that deductive reasoning is actually overlooked. It's an overlooked component of mathematics education, both at the school level and even at the university level. Now, you might think, how is it possible? There are proofs that are done at the university. So certainly deductive reasoning is there because that's what a proof is. A proof is a structure of argument, is an argument that's built out of deductive reasoning. But the thing is that most of the times, proofs are learned. the students learn the proofs for the exam most of the times. They don't really understand logically why does a certain line follow from the previous, and there is little chance to check whether they understand or not, because in the exam, when you ask them to give the proof, there are two possibilities. Either you ask them to give the proof of a theorem they've seen before, which is in most cases you do that, or you ask them to give a proof for a theorem they haven't seen before. Now, for the second part, it occupies a small fragment of the total mark, and very, very, very few students end up getting that right. But now, the other one, where you ask them to produce a proof of a theorem they've seen, and they've even seen the proof in class, they could have learned the proof by heart instead of actually understanding how does one line follow the other. I remember I had a probability theory exam when I was at university, and I told the lecturer, look, I don't remember this proof. It was in the exam, I had to produce the proof, and I said, I'm too tired to come up with the proof, but if you show me the proof, I can explain to you how each line follows from the other one. And it said, okay, and then I managed to do that, and he was quite happy with it. Now, so let me say just a couple of more things about the deductive reasoning. So what is deductive reasoning? It's in opposition to inductive reasoning. For instance, when you have a pattern, 1, 2, 3, and then you ask, what's the next number? What's the next number after 1, 2, 3? Any suggestions? What's the next number after 1, 2, 3? 4. Yeah. So that's an example of inductive reasoning. It didn't have to be 4. It could have been 7 as well. You can look up on Encyclopedia of Integer Sequences, which gives all possible sequences that combinatorists have come across with in their research. There's like 20,000 entries for sequences starting with 1, 2, 3. There are at least 20,000 ways that people have researched that 1, 2, 3 can continue. So inductive reasoning is when you come up with an answer that's beautiful, that's most natural, perhaps. It's a very human thing. It's not a mathematical thing. You cannot mathematically claim that the next number must be 4. While deductive reasoning is when you have mathematical certainty that the conclusion you're stating is the only option. That's deductive reasoning. And that certainty is very important because in some sense, pure mathematics is all about that. The contribution of pure mathematics to humankind is the ability to be certain. Everything else is already there in applied sciences. And here is one little riddle to explain deductive reasoning one more time. Some of you, I've already shown this to some of you. X plus 3 equals 5. The solution to that is x equal to 2. Now, my question to you, how do you know that x equals 2 is the only number that solves the equation? How do you know there is no other number apart from x equals to 2, such that x plus 3 equals 5? Well, some people will say, okay, we can test other numbers, but now how long are we going to test, right? So I'm going to leave this for the questions question session for you to try to answer this question. I'm sure most of you will get it right, but we never talk about this. We never talk about this at school. We never talk about this at the university. And when I see foundation students in their second year, when I show this to them, they need a bit of time to figure it out, which is a proof that we never talk about these things. I think I've reached the end of the presentation. Thank you.
Thank you very much, Zurab. Are there any questions? And maybe the participants online can raise their virtual hands and we can give them the opportunity to ask it just now. Mesias, you want to start?
Thanks, Zurab, for a very interesting talk on how mathematics should be taught. I really enjoyed the first few slides, where especially the one that you said, students should be assessing mathematics in the way you assess the skills rather than the right answer. I'm in the mathematical sciences. I teach a student that probably going to be working in a bank or managing a portfolio, but I normally teach mathematics. And if I'm teaching the skills, or if I'm assessing the skill of these students, but not carefully looking at the final answer, there'll be a problem, because if these students will go in the professional career without knowing how to compute the exact answer, then say managing a portfolio of say 1 million, but they will come up with an answer say of 900,000 with the, and at the end there will be arbitrage in the market, and they might end up even being fired. So is do you really mean from the mathematical theoretical point of view that students should be assessed from the skill point of view rather than the answer, or from all mathematical sciences field? Thank you.
Thank you very much for that question. So there are two kinds of mathematics courses. Ones which develop that machine type of ability in a human being, which, by the way, is less and less important nowadays with the existence of a computer. So if that's the goal of the course, to learn how to apply the algorithms and get the right answer, then of course it must be assessed based on that, if that's the goal of the course. Here, I'm more focusing on almost like I don't want to say pure mathematics course, because applications can also be discussed in courses like this, but I'm talking about courses which look at the insight, at the mathematical insight, at mathematical thinking skills and so on. And there, if you focus on answers too much, then you end up missing out on teaching the mathematical skills.
Any more questions? Here we go. I will do my 10,000 steps today.
Thank you, Zurab, for the nice talk. I really enjoyed it, but I want to ask one simple question, especially on, I think you referred to I think Professor Jonathan, something like that, of his talk, when he said, like, he tried to address the question, why do most students fail mathematics? And one of the reasons that, if I remember correctly, he said was because of like kids have that fear of failing math. I don't know if you try to address that, like to find the solution for that problem also.
Yes, thank you very much for that question. So I think this actually related to the previous question, because when your mathematics class is no longer about the answers, then this fear starts to go away. This is something that Zia touched on in her feedback. She was saying that in this foundations class, it's okay to make mistakes, and the lecturer is also patient and takes into account different pace of different speeds of thinking for various learners. So I think once we move away from answer-based mathematics to skill-based mathematics, that fear will eventually go away, because you will no longer be judged by the small figure you put in your test. I think that fear a lot has to do with getting wrong answers in tests. You'll be rather judged by your engagement and your conversation, and so yeah, that's at least my experience, that problem can be solved by moving away from answers and looking at skills.
Please.
Zurab, thank you. It was a very exciting talk. You mentioned the idea that set theory. Thank you for commenting on why it was a failure in South Africa. I think the same thing happened elsewhere. I don't know how many people remember set theory in schools anyway. But you mentioned that you believe it is a foundation for developing mathematical thinking. Are there also other parts of mathematics that that could serve as a foundation, or is there something special about set theory as a foundation for learning mathematical thinking? I mean, we all understand why set theory is a foundation for formal mathematics, but does that automatically make it foundation for learning mathematics?
Thanks a lot for this question. I don't think that that automatically makes it foundation for developing mathematical skills, but let me try to give my answer to why I think that it is a foundation for developing mathematical thinking. I think this is actually something that goes back to my discussions with Sophie Marquez. We even wrote an article for, about that on the Sarco magazine. So we were talking about what's the most basic mathematical ability. Where does mathematics start? And we kind of arrived to this answer, which I think each of us already knew beforehand, but confirmed with our dialogue as well, that one of the fundamental abilities of our thought is the ability to consider a collection of things as one thing. Make a list and think of it as one list. So when a few things are now seen as one thing. My classroom, my classmates are the people I see in my class. My classroom is one entity that has components in the classroom. So this ability of our mind to gather few things and see that as one thing in our thought process, I would say is the most fundamental ability of thinking. And that's what set theory is. It studies, it mathematically analyzes this process of forming one thing out of several.
I think there is a question in the chat. Maybe you would like to comment on that.
So should I read the question? Yeah. From Keegan Anderson, thank you for the talk, Professor. One comment: we should also work on the synergy between theoretical and applied mathematics and the education of both. Theoretical and applied mathematics are two sides of the same coin, but form part of mathematical sciences. I completely agree with that, Keegan. And that's why also in these mathematical explorations examples that I showed you, it was all about linking mathematics with real life around us. So when I talk about these things here, I'm envisioning a mathematics program where both pure and applied mathematics are together. And the way applied mathematics comes in there is through the contact with the real world. And the way pure mathematics comes in there is through the thinking processes that emerge as a result of this contact. So I completely agree with Keegan there. There is another question.
Okay.
I'm just curious about our colleague here from statistical and actuarial sciences. His example of the precision needed in his subject. How would your students answer the question, how do you know that you're right? What would they do if you ask your students to say, how do they know their solution, their answer is correct?
The quick answer is you ask ChatGPT.
Then I look at what Zurab said. I look at the skills of yes, then they will provide the ways of how to get to the answer. Yeah, and then I take that into account.
Yeah, it's an interesting point. So they will provide the ways of how to get to the answer. In many cases, this will be a methodology they've learned. They will not be necessarily able to scrutinize the methodology and claim for sure that it does give the right answer.
But I think that follows on from what you were saying earlier about where your marking had intuition. That's what I try and teach my students is when you get to an answer, even though your calculator says this is the answer, you have to look at it and go, does my intuition tell me that this is the right answer? So you have to, that's one of the mathematical skills surely that you should be developing, is a mathematical intuition to say, is the answer correct or not?
Thank you. Yes, that's I completely agree on that. Intuition not only allows us to get to answers, but also to verify and confirm that they're likely to be right. It's very important in mathematics.
Any more questions? I think there are no questions online. Then Zurab, thank you so much for your talk. You gave us, sorry? Okay, sorry, thank you.
I see that there is also a question from Farai, but maybe first we give a chance to Zeki.
Zeki, you're welcome to ask your question.
Oh, thank you very much. Can you hear me?
Yes.
Yes, we do.
Yeah, it's actually not a question. It's just a comment, which is an addition to Zurab's answer to the first question, which was about getting a correct final answer. I think Zurab's point is that the skills involved in finding or calculating the final answer are very important, and hence they should be assessed, because this is what make up the process, the way to the final answer. But he does not necessarily mean that the final answer is not important. But if you work on the skills required to establish or build proofs or make calculations, then one has a better chance of getting the final answer correct.
Thanks very much, Zeki.
Thank you, Zeki. Zeki was actually my set theory lecturer at University of Namibia. And yeah, so thank you for that elaboration explanation. Yes, so Zurab, I have one question, or maybe just a comment. We've spoken about this, that when I was in Australia, I interacted with a lot of people, students from law faculty. And in Australia, they have a course on set theory of foundation mathematics, where they teach students that are doing law. Do you have any plan of introducing this course in law faculty here in Stellenbosch?
Yes, I do. I'll first together with you. And there is a comment also by Farai Mlanga. I want to check whether you take into account students' mathematical background and the diversity in your classroom. That's actually another very important point that I didn't include in my talk, which is that the lecturer should constantly be trying to read and understand their students. And with every single interaction with a student, you're getting more and more information about them. And this is very important in your teaching. In a big classroom, when I ask them to answer some questions, there are some students who always raise their hands. After a few times, I tell them, it's expired, you can't answer anymore. Now others need to answer. So I try to, yes, Farai, thank you very much for your comment. I do try to do that. And maybe in another talk, I'll give a separate, dedicate a separate slot for that aspect of teaching and learning mathematics. Thank you.
Okay, then Zurab, thank you very much. A big thank you to all of you and to the online participants.